Nuclear fission is a powerful process in which the nucleus of an atom is split into two smaller nuclei, accompanied by the release of a large amount of energy. This process can occur spontaneously in certain heavy and unstable elements, or can be induced by bombarding the nucleus with neutrons. Nuclear power plants utilize controlled fission reactions to generate electricity. The energy released during fission is harnessed to produce steam, which drives turbines connected to generators. Fission is also a key component in nuclear weapons. Understanding and harnessing the potential of nuclear fission have revolutionized energy production, but also raised concerns about safety, radioactive waste, and non-proliferation of nuclear weapons.
Nuclear physics studies the nucleus of the atom, that dense, compact, and explosive place where most of the mass of matter resides. Here, everyday laws do not govern, but rather fundamental forces. The strong force, which binds protons that should repel each other, and the weak force, which allows neutrons to disintegrate. Studying the nucleus is like entering a world where grams equal tons of energy. A single atom can unleash more force than a complete chemical reaction. Nuclear physics not only explains bombs and reactors, it also explains stars, natural radioactivity, diagnostic medicine, and the dating of fossils. It shows us that the most brutal energy is hidden in the smallest things, and that the nucleus, though minuscule, has the power to transform the world.
Why is nuclear fusion better than nuclear fission? Nuclear fusion and fission are two different processes that can release nuclear energy, but they do so in fundamentally different ways. Nuclear fusion offers several advantages over fission, which makes it a potentially superior source of energy. Fission, the splitting of heavy atomic nuclei into lighter ones, has been harnessed for decades to produce electricity, but it comes with drawbacks. It generates long-lived radioactive waste that poses a storage and environmental challenge for thousands of years. Fission reactions require critical mass of fissile material and are inherently at risk of meltdown accidents, as seen in Chernobyl and Fukushima, which have catastrophic consequences for human health and the environment. In contrast, nuclear fusion, the process that powers the sun, involves combining light atomic nuclei, such as hydrogen, to form heavier ones, releasing vast amounts of energy in the process. Fusion promises a nearly limitless supply of energy, drawing from abundant fuels like deuterium and tritium, which can be extracted from seawater and lithium, respectively, ensuring a vast resource base compared to the limited and geopolitically concentrated supplies of uranium for fission. This abundance can lead to greater energy security globally, as countries can access fusion fuel more easily than uranium or fossil fuels. Another advantage of fusion